Thank you. Our distinguished guests, it's a great pleasure to have you all here today. This is a very special event for us, and many of you have traveled from some distance is indeed very important for us. So I would like to again thank you for your participation, and I sincerely hope that you will enjoy today's workshop. And with that, I am happy to start our first plenary talk session. We are going to have two speakers in this first session. Our first speaker, I'm very happy to introduce him. He is Professor Dr. Ramon Codina from Technical University of Catalonia, UPC in short, from Spain. Dr. Codina is Professor of Continuum Mechanics and Structural Analysis at the UPC, where he began his academic career in 1990. He teaches courses on continuum mechanics and mechanics of structures, as well as courses on computational mechanics and functional analysis in mechanics. His research is concerned with the development, implementation, and numerical analysis of finite element methods applied to physical problems in engineering, mainly in fluid mechanics, but also in solids and in electromagnetism. He has directed 18 doctoral theses, and he has published around 200 articles in indexed prestigious scientific journals. He is responsible for the research group Numerical Analysis and Computation that is identified as a group of excellence by the Universitat de Catalunya. Much of Professor Codina's research is motivated by technology transfer projects. In particular, he has participated in 22 European Commission projects and 16 projects funded by Spanish ministers. And in a quite number of them, he is the principal investigator and the main researcher. His current projects deal with aeroacoustics, transport of particles of fluids, viscoelasticity, and optimization of aerospace profiles. In recognition to his research, Professor Codina has been invited to give several plenary lectures, 27 in total. He has received a number of important awards, among which the Brandt Medal in 2018 and the ICIA Academia Award. Every 5 years he has received this award. The last one is in 2021. And the IACM Young Investigator Award, also the GL Leons Award to Young Scientists in Computational Mechanics, and the Distinción de la Generalitat de Catalunya a la Recerca Universitaria. So let us welcome him together to have his talk entitled Hybrid Intrusive ML-based Reduced Order Model for the Optimization of Aerodynamic Profiles.
Okay, so first of all, thank you very much for the invitation. It's a pleasure to be here. Today we'll talk about a topic that should be framed in the field of scientific computing. You know, in this institute we have a number of topics, and maybe this topic will be framed in this one, in scientific computing. So I didn't really know which was the depth of the talk, since this is intended to be for a wide audience. I'll talk about the reduced order models and the interaction with machine learning techniques. I'll try to do my best to make it not very technical, let's say, although the details are obviously technical. So this is a work that I am doing right now with a student, Zuke Pardar, and my colleague Juan Valles, both from the University of Catalunya Universitat. So this is the outline of the talk. I will make first a brief introduction. I will try to explain the role of reduced order modeling in optimization, and in particular in the optimization of aerodynamic profiles, just a simple idea. I will explain a bit the concepts of proper orthogonal decomposition in reduced order modeling, so it's a type of reduced order modeling. I'll talk about stabilization that is needed in the case in fluid mechanics. We have two variables in play, velocities and pressures, and also where we have the possibility of having convective dominated flows. Then I will move to the role played by machine learning in reduced order modeling. In particular, I will start talking about models that rely only in machine learning techniques. So it is possible to design reduced order models that are purely driven by data and using machine learning or artificial intelligence techniques. Then I will present our hybrid model. So this is our contribution. I'll try to be more or less general when talking about these topics. And here I will present our contribution, so our hybrid model. I'll show a couple of numerical examples, and then I will conclude. So let me try to motivate why to use reduced order models. I mean, the reasons why they may be needed are numerous. So a reduced order model is a model that is constructed after we have, let's say, a fine simulation, what is called a full order model. And from that full order model that may have millions of degrees of freedom and that is very expensive, from that full order model we want to construct a reduced order model with a few degrees of freedom, maybe tens of degrees of freedom or even less in some cases, and then do calculations with this reduced order model. Okay? So maybe the simplest example for those of you that know a bit about structural mechanics is the model analysis, not only the structural mechanics, but in general in wave propagation problems. In structural mechanics, for example, you compute the eigenloads and the eigenvalues of the system to be solved, which is a second order different system in time. And from that, you can construct models with a very reduced number of degrees of freedom, maybe 2 or 3 or 4, at most 10, I would say. So that's the idea of reduced order models. And there are many problems in computational mechanics that require to solve a given problem many times, maybe with a little change on the parameters or the boundary conditions or whatever. Maybe the paradigmatic example of this is optimization. In the case of optimization, you have to evaluate many times the cost function, and when you evaluate the cost function, you have to solve the problem. So you have to solve the problem that you have at hand. And then in this case, for example, it would be very interesting to have a reduced order model instead of a full order one. That's what I said here. Another particular case of optimization is the case of the shape optimization, which is the one in which we are interested now, in which you parameterize the geometry of the profile, for example, and then you optimize the parameters of the profile according to a certain target cost function. For example, the drag. You want to minimize the drag. That's a typical example of optimization in aerodynamics. Well, that's one thing. So we need a reduced order model, and that's interesting. So, but those reduced order models are coarse and sometimes not very accurate. So the idea of our motivation is to correct those reduced order models, so to introduce a correction to make them more accurate. So that's the idea. And what's the idea of our way to do the correction? So the way reduced order models are constructed is usually from solutions of the full order. So some fine solutions are known. The most classical example is the POD model that I will explain, the proper orthogonal decomposition, in which you have the solution at several time steps. These are the so-called snapshots. And from that solution obtained at several time steps, you construct the reduced order model. But the important thing is that we have at our disposal fine solutions, the solutions of the full order model. Okay? We call them fine, from fine discretizations, let's say. So now the idea is to improve the core solution, the reduced order model, from the knowledge of the fine solution, because we have them at our disposal. We have those fine solutions at our disposal. So this is in general a convenient strategy and sometimes necessary. This is necessary in the case of in which the core solution is unstable, that might happen, or also in the case in which the core solution fails to satisfy a basic physical principle, for example, equilibrium in mechanics. So when you go from the full order model to the reduced order one, the solution doesn't satisfy a basic principle such as global equilibrium. In this case, a correction might be needed, and we have to remember to do that correction that we have at our disposal the full order model solution. So what's the role played by machine learning in reduced order modeling? In general, classically, I would say, reduced order models involve the original equations to be solved. That means that they are constructed from the original equations. We will see how. Typically from the Lurkin projection or also from other projections. But typically you start from the equations you want to solve, you project them onto the reduced order space, and then you get the model. Those models are called intrusive because, I don't know if it's a correct word or not, but they are called intrusive because they use the original equations you want to solve. However, we have a priori information, what I call here a priori information, which is the fine solutions, as I said before, the snapshots, and sometimes also physical insight. So we know the physics, and we know how the solution should behave, and maybe even experience or experiments even. So we know the solution of the fine problem maybe sometimes through experiments. That's information we have. So the solution of the full order model, the experiments, the physical insight, whatever. So all this is a priori information. So the point is that sometimes reduced order models can be created only with this a priori information using machine learning techniques or artificial intelligence in general. So these models that don't make use of the equations to be solved are called non-intrusive. Okay? So on the one hand, we have models that use the equations to be solved, that are called intrusive. So those are the classical models. And on the other hand, we have an amount of data, maybe we have sometimes a huge amount of data, and we want to use this data to create a reduced order model using machine learning techniques. Okay? And those are the non-intrusive models. In the middle, of course, there are what we can call hybrid models that use both the original equations, so they are intrusive in some sense, but they also use techniques of machine learning to profit from the a priori information. Okay? So we may profit from the a priori information. We have experiments, the fine solutions, physical insight, whatever. So I will talk about a couple of hybrid methods, but I will also talk in this section about our proposal, which is a hybrid, an intrusive model, corrected with a term that uses a neural network to create that correction. Okay? And that uses the a priori information that I mentioned before to correct the original intrusive model. Okay, so let me go to the role played by reduced order model in optimization. This is just an idea. It's very simple to understand. So in any optimization problem, and particularly in aerodynamics, you have to evaluate the cost function many times. So which is the idea? The idea is that you can use a high level language for the optimization. Here I said at MATLAB, but in our current implementation we are using Python. So you have a high-level language in which you code the optimization scheme, the optimization algorithm. And then when you have to evaluate the cost function, which is the really expensive step, then you call your computing code, let's say your compiled code. And that compiled code, in our case it's called FEMUS, it's our in-house code. That compiled code, in fact, has two stages. One in which you have an offline calculation in which you construct the ROM model from the full-order model solution. So you have a full-order model solution that is, in general, very expensive. From that full-order model solution, you construct a reduced-order model basis, for example, and you have the ROM model created beforehand in the offline, in the so-called offline stage. And then when you evaluate the cost function many times, instead of using the full-order model, you use the reduced-order model, okay? And then you get the results that you want to optimize, for example, the drug. Okay, so this is a very general idea that can be applied to any optimization process, in particular to shape optimization of aerodynamic profiles. So this is a classical benchmark, just to show what you can get. This is a profile made with the two circumferences joined by this straight line, and you have a flow from the left. So this, in this case, we have two parameters. One is the angle of attack of the flow, and the other is this length, normalized somehow, and you want to minimize the drag. So well, that's the contours of velocity magnitude and of pressure. That's irrelevant, but I wanted to comment on these curves. So first, of course, the angle of attack, the optimal angle is 0 to minimize the drag. That's what we get. And concerning the length, normalized with the reference 1, the curve that we get for the drag is this one. So there is a minimum and there is an optimal point for the drag. But the important curve, I would say, is this one. So this curve corresponds to the error in the optimal drag, the error that you do in the optimal drag for several number of degrees of freedom in the ROM basis. So you see, by the way, in this case, the reduced-order model had about 10,000 degrees of freedom. So here, in the case of using only 5 nodes, 5 degrees of freedom for the ROM basis, you get an error which is approximately 0.2%. Okay, so this is indeed very, very accurate. Only with 5 degrees of freedom. If you go up to this is 20, 30, 30 degrees of freedom, 40 degrees of freedom, you get an error which is, I would say, 0.02. Okay, so the error is very small. So it's really worth, that's the message, it's really worth to use a reduced-order model in optimization. So that the application we have in mind is the optimization of the profiles of the blades in rotating devices. Okay, so the message takeaway is that reduced-order modeling is very useful in optimization. That's it. Okay. So let's talk a bit about a particular reduced-order model, probably the most well-known and the most popular one, which is proper orthogonal decomposition. So what is the idea? The idea is the following. The idea is that we have a time evolution problem that we want to solve, for example, in compressible Navier-Stokes equations. U is the unknown, which has several components. That's the time evolution of U. This is a nonlinear differential operator in a space, general nonlinear differential operator in a space, and this is the right-hand side. So here we have position x, time t, and maybe a set of parameters mu, or maybe a single one mu, that defines for example, the Reynolds number. Or in the case of shape optimization, mu, the parameter, also determines which is the geometry in which the problem needs to be solved. Okay? So that's the continuous problem, general arbitrary partial differential equation. First order in time, this is important. I mean, you can always transform an equation to a first order equation in time. Once you discretize in space of linear time, of course, once you discretize in space, you get a system of this form, where now capital U is a vector of unknowns, and is the matrix that arises from the temporal derivative, is the so-called mass matrix. Then you have, in general, a nonlinear operator multiplied by the non-zero coming from the spatial operator on the right-hand side. And then you need to further discretize that in time. So you need to discretize the temporal derivative in time, and at the end you get a nonlinear algebraic system of equations to be solved. So this is just to fix the notation. So what is the proper orthogonal decomposition? The idea of the proper orthogonal decomposition is the following. You collect the solution at several time steps. Here, for simplicity, I have considered that the time steps are 1, 2, up to ns, but they could not be consecutive. So you collect the solution, and for technical reasons, for stability, you subtract the mean. This is not really relevant. So you collect the solution at different time steps. And then what you do is the singular value decomposition of this matrix of steps. This is also in some other fields, it is called the principal component analysis, exactly the same. In the context of reduced order modeling, it is usually called proper orthogonal decomposition. So you do the singular value decomposition of this matrix, and from here you get a matrix that contains the left singular vectors, the eigenvalues of the singular values, the diagonal matrix that contains the diagonal values, and the right singular vectors. So this is an algebraic operation that is done in many cases, in many applications. It turns out that these matrices, the left eigenvectors and the right eigenvectors happen to be orthogonal. That's important. In different spaces, because one has this matrix is a matrix that has the total number of degrees of freedom as dimension, whereas matrix V, the right eigenvalues, eigenvectors, have only the number of snapshots of dimension. So the dimension, this S means the number of snapshots that we have, that is much less in general than the number of degrees of freedom. And we can organize the eigenvalues in this way, so that they are decreasing in magnitude. Okay, you can take out the eigenvalues that are 0 and obtain the so-called reduced singular value decomposition. It's essentially the same. And from the matrix of left eigenvectors, we can construct two spaces. One space that is the one that is spanned by the snapshots. Okay, so imagine we have, let's put numbers. Imagine we have 1,000,000 degrees of freedom in the full order. 1,000,000 degrees of freedom. And then we take, let's say, 1,000 snapshots. Okay? So that would be a space of dimension, if these are linearly independent, that would be a space of dimension 1,000. And then from these, we take the first eigenvectors, and we define a space that is going to be the reduced order model space that has only very few number of elements in the basis, maybe 10. So in the full order model we might have millions of degrees of freedom. In the space spanned by the snapshots, maybe we have a dimension of the order of several thousands. But when we go to the reduced space, that has a dimension of the order of 10, let's say, 20, 100, but not more than that. Okay? In fact, the quality of the approximation of this space with respect to the space spanned by the snapshots is measured by this quantity that is called the relative information content, that is nothing but the sum of the eigenvalues up to R, the dimension of the reduced space, divided by the sum of the total number of eigenvalues. And the amazing thing is that that number goes to 1 very quickly. So this is an example. This is the example of singular eigenvalues and the relative information content for the problem of the flow of the cylinder. Just one example, solved using the finite element method. But for this particular case, you see, using just a few number of POD modes, you get the relative information content that is very close to 1. Okay, so that gives us some theoretical basis, some theoretical ground to know that what we are doing makes sense. In fact, we have this general theorem that states that the singular value decomposition is the best approximation of rank R, the target dimension of the reduced space to the matrix of snapshots S. Okay. Okay, so which is the reduced problem now? That's simple. Once we have the reduced basis, we approximate the solution in terms of the reduced basis. As I said, we have here 10 degrees of freedom, plus the mean, because for technical reasons I said that we have to subtract first the mean and then we have to add it. Then we plug this into the original system. Remember that the original system was AU equals R. So we plug this in the original system and we get this equation. Of course, this equation is overdetermined because maybe we have 1,000,000 equations and only 10 degrees of freedom. So what we do to have a determined system is to project that equation into the wrong space. So we multiply by the transpose of the matrix of left eigenvalues, and we have this reduced over. So that's the problem that we have to solve at the end. Okay? So this is the idea in terms of what the POD-ROM method is. Okay. Just a word about interpolation. In fact, I have deleted this slide about interpolation. In the case of in which you want to interpolate from different values, you have to be very careful because the manifold in which the solution lives is not a linear manifold, and then you have to be careful about that. But that's a word of warning that I wanted to include here. Okay, so that's the idea of POD-ROM. Let me talk about a method in which we have been working for several years, which is VMS. VMS stands for variational multiscale, applied in general to the full order model. We have applied that to the full order model, but it turns out that it is crucial to apply that to the reduced order model as well. And I will try to briefly explain which is the idea of variational multiscale stabilization. So the idea is the following. So this is the equation that we want to solve, okay? That's the question we want to solve. The same that I introduced before. Suppose that the operator Ln is a general second order differential equation. So we have second order derivatives here, first order derivatives here, and here. I have distinguished them because one term is integrated by parts and the other is not. And then the zero order term here. And that is a semi-linear operator in the sense that derivatives are linear, but the coefficients may depend on the solution. So in fact, in the problem we have in both the slots of operator n we have u. So that means that the operator is in fact non-linear. So in the finite element method, that is the method that I will use as full order model, we have to obtain the weak form. So we test this equation by a test function v. We integrate by parts, and without going into the details, at the end what we get is this variational equation, okay, plus boundary conditions. So that's the weak form, that's the important thing. So we can skip that and you can go directly from the blue equation, blue continuous equation to the blue variational equation. So what is the idea of a variational multiscale method introduced by Hughes in the 90s? So the idea is that the composition of a continuous space, so this is the continuous space, into the space of the finite solution, in our case it will be the finite element space, plus a remainder that we will call the space of subgrid scales. So that's the idea. Essentially, that's the idea. That's splitting. You insert the splitting of the unknown into uf plus u prime everywhere. The temporal derivative, by the way, this is already a discretization of the temporal derivative. You insert the splitting in the temporal derivative, in the nonlinear term, in the linear one, and so on and so forth. You first test the equations with the test function in the full order space, which is this one, and then you test the equations in the complement v prime, the space of superior scales. Of course, there is no approximation here. It is exact. This, I would say, is just a way to write the original equations. And now the problem comes in the way to approximate the space of superior scales, and in particular in the way to approximate this equation, because we don't want to solve the equation for the superior scales. We only want to solve the equation for the finite scale, for the full order model scale. for the scales that can be resolved by the discretization, in our case, finite elements. So here we have to make several choices and approximations. The first choice is that we take this particular one of our group, we take this space of simplicities scales as the one that is orthogonal to the full order model. We call that orthogonal simplicities scales. The main approximation, in fact, is to approximate the operator n when you apply it to the simplicities scale. That is the key approximation. Okay, and of course I will not enter the details of how to motivate that, but that can be motivated. Okay, you can motivate that approximation somehow. And then there are a couple of technical definitions, what we call dynamic simplicities scales, or not, or quasi-static, linear or non-linear, and what happens on the interior boundaries, but I will escape that. So this is an important approximation, and this is also relevant for what I will say. So the point is, message to take away, not the details, splitting of the solution into finite solution plus simplicities scale, and then approximate the equations for the simplicities scale somehow. Somehow, that's the only thing we can say so far. And at the end, that allows you, what the important thing is, that allows you to take the simplicities scale u prime in terms of uf and plug it back to the first equation and obtain a problem in terms of the finite scale only. And that's what I have written here. So at the end, what we have is a modified equation where Bf is a modification of the original semi-linear form, which is given here. It has the contribution from the original fine full order model solution, let's say the finite element solution, plus a contribution B prime that comes from the dependence of the simplicities scale onto the full order model solution. Again, message summary, the summary of this. We split the equation into finite element equation and equation for the simplicities scales. We approximate the equation for the simplicities scales and plug the result back into the finite element equation. The bottom line is that produces a modified problem that is enhanced, that has enhanced stability and accuracy with respect to the original converting method. That's it, and that works in many problems and in many contexts, and in particular in fluid mechanics. So this is this slide. In fact, these two slides are a topic in which we have been working for several years in different problems, for different operators N, for different Wagner forms F, and so on. What we have done more recently is to extend this idea to reduced order modeling, and we have ended up with a method that we call VMS model. So first a comment. So that is important to keep in mind that many people is using in different forms. So we have two splittings. One is the splitting that I have mentioned a minute ago, which is the splitting of the continuous space into the space of the fine solution plus the space of the simplicities scales. But also in reduced order modeling, we have the space of the reduced order model plus another complement. That would be the complement of BR in BC. Okay? And imagine that BR is the space spanned by the left eigenvectors that I mentioned before in the case of POD, proper orthogonal decomposition. Suppose that we have a basis, this is in general not needed, but suppose we have a basis for the full order space obtained from the left eigenvectors. I mean, we never construct the vectors from R up to NP, but suppose we have them. If we have orthogonal scales, we have an explicit representation for this space. What would this space be? Since we know that the basis, the left eigenvectors, are orthogonal, then this space B double prime would be the vectors that are left aside from this construction of BR, so the vectors that have been discarded, so from R plus 1 up to NP, plus the orthogonal complement to BF. Why? Because we are using orthogonal split scales, as I said before. So the good thing about using orthogonal split scales is that we have this explicit representation of complement to be double prime. And now the idea is, what is our message? The message is that since we have to use a stabilization in the full order model for different reasons, we also need to use stabilization for the reduced order model. And at the end, what we do is exactly the same for the reduced order model as we did for the full order model. Okay, let's move now to machine learning in reduced order model. So, let me explain first what I already mentioned before, the idea of non-intrusive models. So non-intrusive models do not use the physical equation. So the POD model that I have introduced earlier, standard POD ROM, uses the differential equation, the equations of the problem, because we just plug the approximate solution into those equations and then we project onto the reduced order space. So we make use of the physical equations. However, non-intrusive reduced order models don't make use of the physical equations. So how do they work? So if this is a classical reduced order model, so we have the full order model solution, we project it, we solve the projected equations, we advance in time, and then we somehow compute the full order model solution again. In the case of machine learning based models, these projected equations are replaced by a function constructed using machine learning techniques, for example, a neural network, an artificial neural network, and that projection from the full order space to the reduced order space, and also the inverse operation, are also constructed using machine learning strategies. Let me show a particular example, very popular nowadays, of how to construct this projection from the full order model solution to the reduced order model, and also from the reduced order model solution to the full order one. So those are the so-called auto encoders. Autoencoders are just artificial neural networks, nothing else, with a particular property. The number of inputs is exactly the same as the number of outputs, and it has an inner layer, the innermost layer is reduced, is very reduced. It's the so-called bottleneck. It's the bottleneck. And now the loss function, what you optimize is, when you construct the weights and the biases and all the parameters of this neural network, what you optimize is that the difference between the output and the input is minimum. So in a sense, you want to be as close as possible in the output as in the input. Okay, so that should be, at the end should be, if possible, that mapping should be the identity. Of course, it's not possible because in the way you will lose some information, but you want to be as close as possible to the identity. So the first part, when you go from the input to the bottleneck, is the so-called encoder, and when you go from the bottleneck to the output, is what is called a decoder. So the idea is that the mapping that gives you the reduced order solution is the encoder, and the mapping that goes from the reduced order solution to the full order one is precisely the decoder. Okay, so this is a particular way to construct the mapping here and the mapping here. Another way in which hybrid models have been developed, I'm talking now as a first example of a hybrid model, so a model that uses both the equations and machine learning techniques. So those are the so-called closure models. Closure models, there are many types of closure models. Some of them try to obtain the effective physical parameters, others try to obtain the effective physical forces, whatever. I will explain them in general. Suppose that that's the representation of the full order solution in terms of the reduced order solution plus something else. You may call that simply the scale in the full order space. So suppose also that we can split the original differential equation into those two equations. Okay, so we can always do that, for example, assuming those two spaces are orthogonal, as they really are in proper orthogonal composition. In fact, the classical reduced order models, what they do is they simply neglect the subscale component. So a family of closure modeling consists in adding to this system a closure that depends on the reduced order solution, and that is modeled somehow using machine learning techniques from what I called earlier the a priori information of the system. Well, here there is a picture of the evolution of the full order solution, the reduced order solution, the projected full order solution, and the closure error. That's what we intend to model, that closure error. Okay, so a second example of a hybrid model, very popular nowadays, which is the so-called physics-reinforced reduced order model. So what is first of all, what is a physically informed or physics-informed neural network? A physics-informed neural network, assuming that the problem that we have to solve is AU equals 0 for simplicity, just, I don't know what I wrote here, I could have written R as I did before, anyway. So a physics-informed neural network is a neural network, any neural network you want, in which the loss function is the residual of the equation you want to solve. Okay, so that's the point. The loss function, or the target function, or the cost function, whatever, in the context of artificial neural network, they are called loss functions. So the loss function is precisely the residual of the equation you want to solve. Okay, so this is a hybrid model in the sense that it uses the equations to be solved and also machine learning technique. So this is physics-informed neural networks, and that can be applied to the context of reduced order models as well. In the context of reduced order models as well, what we add is another functional, because by the way, this is applied also to the full order model. I mean, this is a general strategy to design a neural network. So in the case of reduced order models, we can add this functional in which is the difference between the solution obtained by the machine learning technique and the projection of the snapshots. Remember, we have the snapshots. And then we minimize this function. I mean, there are several issues regarding this method, but I just wanted to mention the existence of this technique, the physics-reinforced reduced order model. And finally, I will conclude with the method that we propose. I have several slides here, but the idea, I think, is simple, and that's what I will try to explain. So suppose that we have this system to be solved. So that's the method that we propose now. Okay? So we have this system to be solved. AUR, the reduced order system, equal to F. Now we have to remember that we have at our disposal the snapshots. So the snapshots are still there. Remember, the snapshots were used to create the basis. They were used to create the basis, but they are there. We don't need to throw them to the, let's say, dump them out, okay? So we can still use them. We don't need to throw them out. So that's the system. We know the snapshots, and now we assume that the best possible course solution, the best we would obtain, is the projection of the snapshots at the points in which the snapshots are available. So that's our assumption. So we take the snapshots live, of course, in the full order model space. We project them onto the reduced order model space, and we claim that that's the best we can hope for. I mean, you can agree or not, but that's our assumption. Okay, with this assumption, I will go to the end. What we propose is the following. What we propose is to add to the numerical model a correcting term, the UR, that can be obtained from an artificial neural network, and that artificial neural network is constructed by imposing that the difference between the projected snapshots and the correction that we want to model, this is what we want to obtain, that correction, and the exact correction at the points in which we have the snapshots, because of course, at the points in which we have the snapshots, we know which should be the exact correction. So we want this difference to be minimum, okay? As I said, I don't want to go into the details. We have that published in the context of mesh coarsening, and we have recently submitted a paper on that in the reduced order model. But that's the idea, okay? A few remarks about that, but the idea, as I said, is simple. So we have the snapshots, and we correct the reduced order model by imposing that the difference between the reduced order model solution and the projection of the snapshots has to be minimum at the points in which we have the snapshots. And that corrective term is obtained using a neural network. Let me show a couple of examples in fluid mechanics First is the flow over a cylinder, a backward-facing step. So that's the pressure magnitude and the velocity magnitude and pressure isocontours. Here I will show the results with 7 modes and 26 modes. That's the Reynolds number, so it's the total flow. And that's it. So for example, when we have 7 modes, we have taken a point right after the step in which we plot the evolution of the different unknowns, and that's the plot. Well, it's impossible to see from there. I'm sorry, because the quality of the projection doesn't allow you to see, but here we have the full order model solution, the uncorrected, the corrected reduced order model solution, and the corrected one. It's only possible to see, but the corrected solution fits much better the full order model than the uncorrected one. Of course, the difference is much higher when we only use 7 modes than when we use 26. I'm sorry, but it's impossible to distinguish the pictures. This also happens in the spectra. This is the spectrum in velocities and the spectrum in pressures. The spectrum is much better approximated using the corrected model. And if you advance in time, outside the training time interval, you see the uncorrected solution, which is this yellow, almost impossible to see. I don't know if you guess it. The uncorrected solution simply blows up, and the corrected one stays very close to the full order model. Anyway, I mean, the results are very good, otherwise we wouldn't try to publish them. Well, there is another example, which is the flow over 3 cylinders arranged in a triangular configuration. Again, the same conclusions, but impossible to see here. And I'm sorry for the quality of these pictures. So, a summary. I have tried to explain a general methodology to correct coarse models very quickly. The important thing is the requirement is to have a set of fine solutions for a number of configurations. And those fine solutions are known in the case of ROMs because they are the snapshots. The corrective term and the correction term is constructed using an artificial neural network. And as I said, the training set of that neural network can be taken as the snapshots. The resulting model can be considered a hybrid one because it combines an intrusive model with a machine learning technique. Well, that comment about the methods that we use and other possibilities, other possible extensions that we have in mind, some of which have already been published, like this one. We have already published a paper about that. So those are the papers we have published on the topic. Perhaps the most 2 relevant ones are those 2 here, one that is already published and the other one that is recently submitted. This one that is recently published deals about mesh coarsening, that correction applied to mesh coarsening, and that one is with this correction applied to reduced order models. So thank you very much for your attention.
Thank you, Professor Codina, for this splendid talk. It was very interesting. Let's see if we have some questions. Any questions from the audience? Yes, Codina has a question.
I think I got me. Okay, first of all, I want to thank you for your presentation. Gerek var mı ya bana? Okay, first of all, I want to thank you for your nice presentation. And the question I want to ask is the construction of the target in your IAM. You have the experiment, as I understand, right?
The target where, sorry?
The IAM part, machine learning part. You need to minimize the residual. Yes, that's right. How do you compute the DXI?
Yes, this is the exact correction. I mean, the exact correction is the one that is given here. So this is the system, but at the point, this is the time, let's say, those are the time steps, let's say, in which you know the snapshot. If you know the snapshot, you know the exact correction, because that's the exact correction. If you replace this expression by this one, you know, F cancels with F, A, let's say, cancels with F, and you know that the solution is precisely the projection of the fine solution. So at the time steps in which you have the snapshots, you know which is the exact correction.
I see. Okay.
You know, and then in general, this is only true, of course, for the time steps in which you know, or the configurations we call in general. For the configurations in which you have the fine solution, So you know in these configurations you know the exact correction, and then in general you minimize this cost function, which is the difference between the exact correction and the modeled correction.
Okay, thank you. And maybe second question is possible?
Yes.
And okay, as I understand, for the nonlinear part, you are using the VMS. But as I know from the literature, also discrete empirical interpolation methods are quite popular for the ROM. Have you ever tried such approach in this context?
Yeah. No. It's not an alternative, in fact. It's a complement. Because discrete element interpolation deals with a topic that I haven't mentioned, which is hyperreduction. So I haven't mentioned that, but the cost of this system, let me say it here. Where is it? Well, maybe here. The cost of this system, the reduced system, is in fact similar to the cost of the full order model 1 because of the nonlinearity. Okay. So what they endorsed, the discrete element interpolation does, is to bring back the cost of this system to that of the reduced order model by doing some sort of well, it's called hyperreduction. So you further reduce this term to make it cheaper. But they and other hyperreduction techniques aim at reducing the cost due to the nonlinearity. So the idea, let me explain the idea. The idea is that how do you have to evaluate this nonlinearity? Okay, so you have the reduced solution, fine. But here, imagine you use a fixed point method, the Picard's scheme. You have to use U of the previous iteration. So to evaluate this, you take the reduced order solution, you expand it to the full order space, then you construct the complexity, let's say, nonlinear term, and then you solve the reduced system. But that expansion to the full order space increases the cost enormously. In fact, and what they methods do, those PDD techniques are sometimes called, what they do is they try to reduce the cost of evaluating nonlinear terms. But that's something about which I haven't talked.
Thank you very much.
Okay, Professor Codina, thank you very much. I think we have other questions, but we have to wait for the break because of the time limitation. So let us thank